Hello and welcome to our webinar. It's now time for us to start this webinar. This webinar has got the title, A Demonstration of an Interlocking Design Automation Solution, and it's hosted by Prover. Before I hand over to today's speaker, I just want to inform you that you really have the expert now here on the webinar, so take the opportunity to ask questions. If you want to ask questions, there is a question mark icon on the GoToWebinar control panel that you can use. You can type in your questions whenever you want. We will answer them in the end of the webinar, and the other participants will not see your questions. So we will see your questions. You can type in the questions whenever you want, and please take the opportunity to ask questions. So now I would like to hand over to today's speaker, Jesper Karlström from Prover.
Thank you, Lars. Yes, I'm Jesper. I will be with you this half an hour or so. I'm a VP Engineering at Prover, and I've been with Prover since 2008. We will do the following today. First, we will have a demonstration of the full Prover Trident process, the process we propose for doing interlocking design automation. And then there will be some recommendations in the end of this demonstration on what you can do if you want to improve your automation in your process, and also the questions and answers session that Lars just mentioned, about half an hour from now or so. I will not share a lot of theory with you, but we dive directly into a demonstration of a technical solution. And for this demonstration to make sense for you, I'd like to stress a few things about what we are going to do. This demo is based on some mock-up signaling principles that aren't used anywhere in the world, but on the other hand, should be easy to grasp for anyone who has some background in signaling. For example, we have come up with these signaling aspects. And these ones I think you should understand in order for the demonstration to make sense for you. The upper light in each signal is the main aspect, telling the driver if he can proceed or not passing the signal. Red light means he must stop. Yellow light means he can proceed, but with caution, because there is a reverse switch ahead. And then there are three different aspects with the green light, meaning that you can proceed with an unrestricted speed, but you need to be prepared perhaps to stop at the next signal, which is shown by red lower light, or you must be prepared to lower your speed at the next signal, shown by a yellow at the second light, and then finally the real unrestricted one is the green, meaning that you can proceed with an unrestricted speed here and also at the next signal. So as you can see, this is not configurable in any way. It's a generic principle here, saying that if you have a reverse switch ahead, then a yellow light is used. Otherwise, there is a green light if you can pass the signal. This to have mock-up signaling principles suits us well, because the solution I'm about to demonstrate is entirely adaptable to your signaling principles. So there are no principles built into the tools. The idea instead is that you configure the tools to follow your principles, and you configure this using a logic language. I will show a couple of examples of that, but I will not stress that a lot today, because I want to show you the specific application engineering process. So the idea is that if you want, for example, to construct 10 or 20 or 40 interlockings for a particular line, you spend some effort on formalizing signaling principles in a logic language. But when this has been done, you can generate the specific application code needed for each station based on the generic application you have. So again, we are not aiming for a generic application that can be used all over the world. We are aiming for a tool that allows you to configure your generic application, or rather your general signaling principles, to your need. And based on these configuration files with logical expressions, you generate a program for each specific application. The demo will be divided in 3 parts. First is the specific application process, where we configure a station with these mock-up signaling principles. I will show you then how the tool allows you to do simulation, both the interactive way, which is usually done by factory acceptance tests, for example, but also scripted simulation, so you can pre-program scenarios you want to test. And the tool can run all these scenarios, and it can run them in a fast-forward mode, so you don't have to run them in a realistic speed. You can do them really quick. Then I will show you how to make formal verification of this, and finally how to do code generation. When we have some code generation and also have ensured that that the code fulfills the safety requirements by doing formal verification, we need to certify this solution. And for the certification, we have a separate process with a standalone formal verification that I will show you as well. Finally, I will show you a bit from the generic application process. Actually, in the real flow, the generic application process comes first, because you need a generic application in order to generate specific applications. But I find it more useful to start with a specific application process, so you get a better understanding of what we are aiming for. So prepare now for the demo. Let me start here. I start this program called Interlocking, which is the program that we will use for this signaling demonstration. Sorry, signaling automation solution demonstration here. And we create a new project. When we create a new project, we need to store it in some folder somewhere. I put it on my desktop for this demonstration, and I call it something. We can call it test station. Then I need to choose my signaling principles, and I have a lot of different ones here. I will use today demo 3.0. So what you find here is the generic applications or the packages that you have loaded onto your computer. So everyone will have a different list depending on what you have on your computer. I choose to use demo 3.0 for this demonstration. Now, when we have made this choice, this program Interlocking will load all the generic principles. So it includes signaling principles, but it includes also the symbols we can use and various other stuff. This package demo 3.0, it also loads various other packages. So packages can depend on packages who depend on packages and so on to include more features. And there's a list here of everything that has been loaded with the name, version, where on the computer it's stored, and finally where, the checksum of this package. So let me start configuring this one. I will draw a lot, so I choose repeat new objects. I don't have to click so much, otherwise you just pick what you want from this palette here. So let me start by drawing tracks. I want a long track here, and then I want a second track, perhaps like this, and then I want to connect them with switches. So we work like this, like in a painting program. For this demonstration, there is only tracks you draw. You don't add any tables. So that's why we have signaling aspects that depend only on switch positions, no signaling aspect charts or anything like this. I'm done with my tracks now. I want to have a few joints because we need track circuits. So we put out the isolated joints. I want one here. As you see, you have the possibility to choose a name, but I won't use that currently. I think I need a joint here, and I want a joint here somewhere, one here, and then perhaps one here. Okay, something like this. Then I need a few track circuits between the joints. let me put one here, one here, one here. I don't bother about the naming because I think this is only a demonstration, so the names aren't really important. Okay, maybe you saw a mistake. I put one here and one there, so I need to remove one of them. I can remove this one because we want only one track circuit between this pair of joints. Okay, and then a few more things. I want to have some direction objects because some features in the program will probably be named using directions. And then signals. So let me choose signals here. We have entrance signal, and we have some exit signal. So, and it doesn't really matter which side on the track you put it, because there is a little red dot on the track which shows you where the signal is placed from the logical perspective. So it needs to be placed in a joint like this. On which side of the track is not really important. Okay, I think I'm done actually. So I save it. And then I can ask this program to compute now the logic for this interlocking. So what it does, it takes this drawing I just made and it makes an interpretation of this drawing to ensure that it will figure out things like which tracks are in which routes and so on. So for example, when there is a signal, sorry, this is simulator, I close it. When there is a signal here and then a signal here, then it will automatically construct a route from this signal to this signal. And this is not something that has been decided by the program. It's configured in the package I'm using. So for this demo, we construct routes from signal to signal. You might have different principles in your signaling systems. I open up the simulator now, and you can see that the upper lights in each signals here turn red. You also briefly saw this simulated window where you have various information. When I work with this, I'm careful to have two screens, so I can have the simulator on one screen and this canvas on the other screen. For this webinar, I need to simply hide the simulated window between this main window. Okay, you also notice there are some yellow and blue lights here. Blue are a number of nodes, yellow are warnings. So you can see here, it says a few things here about missing information and so on. Also decided by the package what we want to see as warnings. Okay, now I can try the interlocking. For example, I can request a route like this, and then I see the switch throws, it locks, and you get a permissive aspect. I can try now to occupy tracks, like I click on this one to occupy this track. When I occupy the next track, you see that the signal turns to red in the next track, and then I vacant this tracks. And here you get a flashing arrow, meaning that you get a time release of this route. Let me request another route, and let me also request one that we cannot lock because there is an occupancy of the track here. So you see that this route is gray because it's requested, and this particular generic application remembers the request, but this one is green because it's locked. So if the occupancy disappears, then this one gets locked and green as well, and you get the signal. So this is an example of this interactive scripting I mentioned. I mentioned also that there is, if I close this interactive scripting thing, there is the scripted simulator where you have lots of test cases. So for example, you can decide that for each route you want 3 things to be tested. And this one is to test that routes are released correctly after traversal of a train. This one is to test that parallel non-conflicting routes are available when a given route is locked, and so on. And if you want to run, you can look at what tests are done here. Then you see that there, for each route, you try all the parallel routes. And here for each route, you try also this property that they get released properly, and so on. So if you want to run this test for all routes and all signals, you press run. And now we are done with all the tests, because although those are quite many, in particular in reality, this computer has 4 cores and the program utilizes all cores, so you can run the tests in parallel, so you don't have to wait a lot for it. In this case, it took 2 seconds to run the test. If it's a real project, you typically have more tests and more routes, and then it takes longer. But still, it's much faster to fast-forward tests and use all the cores of your computer than to do it in the traditional way. If you want to investigate one of the tests more thoroughly, for example, we can look at the route from G4 to G9. We can open that test, run it. Let me try to fit this on the screen. So I ran it now, and I can look at it. I can run it in real time by pressing real time. So you will see that the route locks, everything is, tracks are occupied, and then the track releases. This one actually also occupies the track after the end signal, so it tests that you get a release in the end of the route. Okay. In particular, this is useful if you have failing test cases, because then you can run through the test until the point where it failed, and it will stop at this failure point, and you can investigate the system. You can even look at values of various variables. So, for example, if we look at the G9, we can do maybe never mind. We can let me do like this. We open it in the real-time simulator, and we look at, and we lock a route. Let me lock something like this one. We can search for G9 to G4 to G9. Clear. To see here that this route is clear, meaning it's locked and something that's usable. And if you wonder what usable is, you can click on this one and you see that there's more things here. It checks something that the tracks are unreserved, for whatever that means. If you wonder, you can click there and you follow the program like this. You can look at the switches with the switch logic and so on. If we now occupy a track, it's not easy to fit on this screen. Let me try it again. Let me occupy this one. And look again at the simulator here. You can see now that the blue line we had disappeared, because this is not, the usable isn't true anymore, and you get a red square pointing out to you where it's not true anymore. So you can look at the preconditions, and you can see that what's not true is that S4 is not vacant anymore, which is precisely what I wanted to happen, because I put something here, this one. Okay, so this is how you can work with and investigate your system, both in this interactive simulation and with a scripted simulation. We also have formal verification. It's shown here. So we have a number of safety requirements specified for this system, and we can run them all by clicking run. So let me do it. Okay, so in this case, it's really quick. It's 400 19 requirements proved in 0.3 seconds. It's very quick for two reasons. First, the number of requirements are not that many. In real-life examples, we can have about 1,000 requirements. Then also the station is not very big. For real-life stations, it's quite common to have proof time of 5 to 10 seconds. Yet it's much less than you normally see if you have generated the logic from some other system. And the reason for this is that if you develop the system, the generic application using the logic language we provide and all these tools, then already the developers can try their application with by running the safety requirements. And when they are difficult to prove, they can change the generic application to make it easier to prove. So in our experience, this makes it much simpler because already the developer will make his design provable by construction, rather than first finishing something, deciding that it shall not be changed anymore, and handing it over to a V&V team who are supposed to do formal verification. That consumes a lot more time. Okay, that's actually the specific application process I wanted to show you. In a real-life example, it would be more of the same, and there would be, for example, tables to configure timer values and stuff. So we decided to omit that for the demo because it simply makes it easier to make the demonstration, and I think you get the concept anyway. If we look at what we did some code, we configured the station, and then this simple demo is only to do a track layout. Usually, in practice, there are also some tables with configuration data to be added. Then we ran some simulation, interactive and scripted, and did some formal verification. I would like to stress that it's important to have good simulation support in order to discover unfortunate choices early. So even if formal verification can be used alone to prove safety, it will not discover if you have made configuration choices that make it, for example, impossible to have simultaneous train routes in the way you want it. Because if something is impossible, it might very well be safe, but it might be bad for your capacity requirements. For formal verification, we'll discover safety critical errors already at the desktop, which is also very good because you don't finish your configuration and your whole specific application process first and then hand it over to a verification team. You actually make the developers run the formal requirements already when they are working, which makes it much less likely that errors will remain in the design. Actually, I forgot to make the code generation, so let me do that. That's easy to forget because it's so simple. The only thing you do is you press this little button. For this purpose, we generate C code. But in many practical applications, we generate code for rail-specific hardware suppliers. So, for example, we have support for Ansaldo Microlock or Hitachi nowadays, Microlock. We have also worked with Siemens Westtrace, Alstom IBPI, and lots of other platforms like this. But for this demonstration, it's C code. Okay, then it's time to look at the certification process. So I mentioned before that the specific application process is only to create the program you want to run on your hardware, but you also need to certify it according to Senelec or something like this. And the certification flow we offer is to use a separate tool called Prove a Certifier. That is a Linux-based tool. So the tool you have seen so far is Prover iLock, which is based on Windows. And the idea is that you generate your files and you perform some work on this, some validation work. and then you put them in Prove Certifier. The 4 input files you need are the ones at the top. 2 sources of the code, simply because by having 2 sources, we use diversified programming to ensure that there are no hidden errors in there. So the first source could be generated source code, as we did with Interlocking, where we generated C code. Or it could be some imported code. For example, if you have written code by yourself, or generated them by some other tool chain. For the second code source, we have been using compiled binary code or a logical code model. So you don't really need, you don't put in the same generated code as in channel 1, but you put in something else that is supposed to be equivalent. And then you add a check in the tool to check that source 1 and 2 are actually equivalent. The safety requirements you want to prove about this code needs to be written and reviewed and approved. But this is done on the generic application level. So if you plan to do 40 interlockings based on the same generic application, you only need to approve the safety requirement once, and then you run the same proof for all the interlockings you have. But for each interlocking, you need also to add the configuration data, that is the track layout and all the tables you want and so on. And this needs to be reviewed and validated on the specific application level, of course. If you feed all these 4 things to Prove Certifier, you will get a proof if everything is okay. So the benefit is that although you need to review the 2 things at the right, you don't have to review or test the code regarding the aspects that are covered by the safety requirements proved by formal verification. So let me make a demonstration of this as well. For this demo, we need, as the second source code, a logical code model. So we can construct it here by, say, generating HLL code model. And then we need also the other 2 things, generic safety requirements and the configuration data. And this is generated by this script. Okay, so now this is the folder I created for my project, and let me close that one. So let's see here, the generated C code, the certification data, and the HLL code. This is what we need to feed to Prove Certifier. In the certification folder, you have both the generic safety requirements and the specific application configuration data. So to feed this to Prove Certifier, which is on a Linux computer, I would like to use a web tool. So I zip this to have this one. And then I visit our Cloud Apps site. So Prover Cloud Apps is a service on the web where you can run various tools. And for example, Prover Certifier for the Trident demonstrators here. So what we need to do is test certification for demo. And then we choose a file. I think it's test station here, and this one test station zip, which we created, and then run. So now you can see here a list of all my runs. I have here demo, a run that I made a bit earlier today when I prepared this webinar, and now I also have new work scheduled here. The test certification for demo. It's scheduled because it will not be run immediately. It will be run when there is when there are free resources on this server. So it's waiting for other jobs. We can see now that it has started, and we need to wait for the output before we're done. I want to stress that although this is some extra thing you need to do, you only do it once. So with the program you saw before, you work with it, you change your configuration, you investigate the system, you debug various configuration data choices that might have been unfortunate and so on. And when this is done, you save everything, you collect the sources you need for the certification, and you zip them and you send them off. So let me summarize here what we did. We collected some relevant files. We ran Prove Certify on the Prove Cloud apps. And if you don't want to use the Cloud apps thing, you can transfer the files to a Linux computer and run them in Linux. What we have not done today is we haven't reviewed the safety requirements and the configuration data, but that's the normal kind of review that you have probably already in your processes. Okay, let me check if we are lucky. This is, we are done, I think. No, not quite. Okay, so it might take some more time. Let me get back to that when it's done then. Okay, I've now gone through the specific application process and the certification process, and we need to look also at the generic application process. It will be really quick because this is not the focus today. I want to show you anyway how we can make changes to the generic application. So let me close this one. And I open the package we have been working with. Sorry, it's called Packages Demo Design 3.0 Generic Design Specification. These are the files used, and I want to show you a few things with changing the implementation of a switch. This is how this logic language works. This is the implementation of how a switch is supposed to work. I will show you some modifications in the locked section here, and also in the section about when to throw a switch to the left. So just first, I want to focus or show you a bit how to read this. So if we look here, this little symbol means not in this logic language. This is an and then this one is an or symbol. So to throw a switch to the left, you need to check that it's not locked, that it has not been placed to the left, that there is no request to throw to the right coming in from the human-machine interface, and that it's not required right by some route. Then you need also either to have a left request or that some route wants it to throw to the left. Okay, so I can, for example, plant a very typical error here. If I say that by mistake I wrote right here instead of left, and I try again here. The first thing, if I reload my project, the first thing I will notice now is that this program will check the integrity of the package I'm using. So when it discovers that there is actually change, it will warn you and say that there are two changes in the package. One is that it finds a new file, which is actually an auto-saved file by my editor that's not supposed to be in the package. And the other one is it says that there has been a change in this implementation of the switch. So this is only to help you ensure that you don't make changes in packages by mistake. Let me ignore that for now. And let's start the interactive simulation. So if we look again at what we just did and analyze what we can expect here. We tempered a bit with the logic for throwing switches to the left. So it we didn't change this path, so it should still be possible to throw it to the left by having a route over it. Sorry, by manually requesting it to the left, but not by requesting a route that requires the switch to the left. On the contrary, if you request a route that requires it to the right, it will be thrown to the left, which is not very useful. So let me demonstrate that. So we need to find a switch that's already to the right here, and I request a route that wants it to the right. Would be this one. Let me do that. Okay, now it's locked immediately because the switch was already locked, which was not my intention. But let me do like this then. If I request this that needs this switch to the right, this one is better. It needs to switch to the left, and I suppose that this will not work now. Yes, because when I request the route, the interlocking knows it needs to switch to the right, but it's used for it needs it to the left, but the logic has been changed, so it doesn't work anymore. But if I throw it to the left manually by clicking it and say through, then it works and the route locks. Now, if we run some formal verification, I assume that this will not be dangerous at all. So all requirements are, yes, they are still green. But because it's simply not a safety issue, it's a functional issue. When the interlocking needs to switch to the left, it doesn't throw the switch properly. But if I run then all the test cases, I will see a number of them don't work anymore. So I can investigate one of them. For example, G10 to G5, exactly the one I tried. So let me try another one, G4, G8. I open it and I run it, and it shows that here the route becomes locked, is failing. So if we look here, we can see that it has requested this one, but it's not locking because the switch is not throwing. Okay. Let me restore this as it's supposed to be. Left instead of right. Now it's okay. And then I introduce some other error. Here, a switch is supposed to be locked if the track that is under the switch is not vacant. This is supposed to prevent you from having switches being thrown under vehicles. So if I comment that out, meaning that it will not be used, and I rerun everything, then we can expect that functions will not be disturbed because everything will keep on working as before, but something dangerous has been introduced because it's now possible to throw a switch under a vehicle. We get the same warnings again that there are changes in this file, but let's ignore that. And let's first run the simulator. As I said, if we just take away the blocking of the switch due to occupancy, it will not make it impossible to request routes and get locking and get it released by trains and so on. So I don't expect any troubles with the simulation. If there is a formal requirement, though, saying that you're not allowed to throw switches under vehicles, then we will discover it with formal verification. So if we run the simulator, it's all green. If we run the formal verification, we find a number of failing requirements. So if we click here, a non-vacant switch must not alter its position. So this is exactly what we changed, that we took away the check of the non-vacancy. Okay. Let me sum up. What did we do? We changed a few signaling principles and investigated the impact. Using simulation, we could show how a small change turned out to have a big unwanted impact. That was the first thing. We introduced, planted a little error and saw that it made it impossible to get roots in certain cases. And then in other cases, we revealed problems using formal verification, problems that weren't found by simulation. We're not focusing on the entire generic application process today because it would be the topic of a webinar on its own. But process-wise, I would say it's not very different from any generic application development process. You need to set up your requirements. You need to have a structured way of implementing them. You need to have some divisional teams between those doing design and those doing safety requirements and so on. What I want to stress, though, is it's much more efficient to make generic application development if you have really efficient and good specific application process, because then you can try a lot of examples and you can discuss concrete effects of what you're doing much more easily. Now to some recommendations if you want to automate more in your process. The first one would be to integrate tools as much as possible. I think it's a mistake to not provide the developers with tools for V&V, but save that for a later stage, because the effect is that when the V&V guys find problems, then the developers already perhaps forgot that piece of the design and has troubles of debugging the design. We also know that having automated code generation without V&V support yields poor results. You can generate code, but it will not do what you expect it to do. So you need to make some V&V tools available to all involved engineers. The old style is to have a dedicated simulator room somewhere in the basement with very expensive equipment. And that one will probably simulate your hardware exactly, or even have hardware in the loops. So I can understand that this is not suitable to hand over to every engineer you have. But if you have a simulator running on everyone's laptop, then there is no restriction on how many seats can have this simulator. The third recommendation would be to be sure to bring your staff on board. One question we often get is, what shall we do with all the staff that are suddenly replaced by tools? The fact is that if you have staff that has worked with you for some time, they are probably by now very good senior engineers who could work with your generic signaling principles. They need to be able to learn how to express themselves in the formal logic language, but when having done so, they can participate in this formalization of the signaling principles. So the result will be that you can deliver more with the same stuff, and you can cover, if someone asks you to participate in a project with 40 interlockings or 20 interlockings, you know that you can do that with the same stuff as you had before, covering much more. Okay. So if you want to start a generic application development, you need to start by writing specifications for the line you want to signal. We have found out that it's very good to divide these specifications in 4 parts. The object model needs to be very precise. From the beginning, it explains what kind of objects you have and what inputs and outputs they have. So for example, for a switch, it might have an input that detects the position of a switch, and it might have an output to the switch motor that throws the switch. These things need to be precisely defined because it's important for all other development you do. Except for that, you can start with design principles, tests, and safety requirements, and they need not be precisely defined from the beginning. You do as good as you can, and then you detail the principles along the way. So you can work in a more agile way for the design principles, the test cases, and the safety requirements. If you don't have the staff to do this, or if you feel unsecure about this, you can let us write these specifications or use some other consultancy firm who are good at this. We would need typically example programs that were made manually to understand how you want things to work. Perhaps you have some drawings, perhaps you have some description somewhere or anything like this. If you hand us what you have, we will try to help you as best as we can with getting your specifications down formally. And you need to allocate an expert who can answer our questions on the way. Then you need, if you want a full signaling automation tool like I've been showing today, you need to formalize the specifications in a logic language. Again, we can do this for you, and you need to allocate an expert who can answer all the questions that arise. Because when you formalize specifications, you need to sort out all the corner cases, things that you normally don't think about when you do normal design, unless these corner cases actually show up in the interlockings you are working with. The first step towards doing this would be to have a meeting. So I suggest you contact us and we have a Skype or face-to-face meeting, 1 or 2 hours, so we can review together your current process and your challenges. And this meeting would be enough for setting up a plan on how to increase automation in your process. We can also have a workshop around this, where you can now learn more about the prove it, try it process and get a roadmap for how you can change your current process. Or we focus on the business case. If you wonder if this kind of automation will pay off in the project you have, we need to look a bit on the project together, and we can decide if it seems to be feasible. Okay, that's all I had to say. So in case you have any questions, I'm ready to answer. Here comes Lars.
Yes, hello, Jesper. We have received a lot of questions.
Nice.
At least some. But please take the opportunity to type in your questions, and we'll start answering now the questions that we already have received from you. So, first question, Jesper. How does the program define the route is between G4 and G9 and not G4 and G6? Does it take into account the direction of the signal? Maybe we need to bring up this on the screen.
I think so, because
so it will
names are rather random. Because the question was G4 to G9 and not G4 to G6. Exactly. So this is again an example of something that has been decided by the package. So it defines the route to be from one signal to the next facing signal, so to the next signal on the same direction. This could be done differently in a different package. It's not a decision of the tool, it's a decision of the package.
Okay, good. I hope that we managed to answer that one. So how are the signaling principles inputted into the program? Can we have an example?
Yeah, the example would be precisely this file. So one principle, the principle for throwing switches to the left is here. The principle for throwing to the right is here. So I prefer to use Emacs, which is a common programming editor, but you can use any text editor for this, actually.
Okay, yeah. All right. And then we have a question about the server. Let's see now. We have 2 questions after each other here. So how the Jenkins server linked with tools? Maybe that one is combined with this one. Will the Linux computer act as an HLL setup? Do you understand?
Not exactly sure, but I think the question is about. I mentioned that we have this.
Yeah, the question I think came when you were demonstrating.
Yes.
Yeah.
So it's you can do this let me put it like this. Prove certifier needs to be run on a Linux server, and we can do it in any way you prefer. So before we just shipped the software and required customers to have a Linux server somewhere and they could run the software. Now we have we understood that some customers, they don't set up a Linux server, perhaps they don't have it, and they think it's a lot of hassle with this. So we set up this Linux server for them with the software on it and provided this web interface. And exactly how the IT setup is, if this is the question about the Jenkins server here,
yeah, maybe
that I don't know. And it's, I would say that we can do this. Sometimes customers have very strong requirements about how to use IT because there might be certification and so on, or policies, and we adapt to that. But in one way or another, we need a Linux server to run this.
Yeah, and I think maybe there's a hidden question there. Why Linux?
Yes, because we wanted to make this compliant with the Senelec EN 50128 norm on the SIL 4 level, and it requires all soft or involved software to be certified if it's not proven in use, or yeah, there are some other ways around, and we decided that running it on an open source Linux is easier for certification purposes than running it on a Windows. That's hidden.
Okay. Yeah. All right. Another question: is there a trial version or demo version that we can download? That's a good question.
Yes, that's a very good question. Yes, you could have what I showed today. Not only by downloading directly, you need to get in contact with us, and we need to discuss a bit how to set this up. And normally we don't just ship the software, we want also to have some contact with you, for example, setting up a little introduction, making sure that everyone knows how to install the software, making sure that people get answers to their questions and so on, because we had some bad experience when we just shipped the software and 3 months later we get the answer that no, we didn't understand how to use it. So,
okay. So software possible, yes, with some help.
For sure, yes.
Yeah.
Yes.
Okay, and then we have another one. Let me see now. Which interlocking technologies are supported by Prover?
Yes, the tools are entirely agnostic with this. So we have actually been adding technologies all the time. So the ones we have for the moment are, let me see, this I take from my head. Siemens Westrace Mark 1 and Mark 2. Hitachi Marklock 2. Alstom IBPI, GE Tempo. GE is also Alstom nowadays, but it's a generic electric platform. Tempo, but also VHLC and Electrologics. Yes, and then C, and I might have forgotten something, but the bottom line is that if you are using something that we haven't been covering before, we are open to add that as a new feature.
Another good question coming up here. What kind of formal methods have you used in this program?
To construct this program, we use mainly, we use a kind of, what should I say? We use our own formal verification to ensure that when we develop things, first we use diverse programming. So we use 2 channels often, and then we have a formal verification that both channels agree. This is how we work.
All right. And then we have a pretty long one here. We write our own our programs in traditional FPD language. FBD language. As the presentation showed, if we use Prover, do we only have to draw the circuit and everything will be automated?
The circuits, I showed something that looks like circuits here, but it's nothing you can draw. What I showed here is only a rendering in a circuit style. So if you have, for example, let me show you here. If we take for the switch, this is how you enter the signaling or the principle for switch when it's locked. You need to enter it in the text-based format like this. But then you can look here what this amounts to for a particular switch, and then you can click here and see it as a schema. And it even shows you in real time, but this is the schema. And you can actually show a number of different styles. But there is no support for drawing schemas like this, because the problem of drawing schemas is if this kind of ladder logic is that you need to do it over and over again. For each switch you need to draw a new schema, which we don't think is good. So it's better to express that generically in this way. And this we can teach you how to do. And then you don't have to draw new schemas every time. There are also some possibilities to actually construct this logic using graphical tools, but this we can discuss. It depends a bit on what you want.
Okay, so we have another 4 minutes before we need to end this webinar. So there's still some time to send in your questions. We have another question, this one. It seems to be a significant initial investment to decide generic signaling principles. When is it worth it?
Yes, this is, in our experience, it's difficult to say because it's different for each customer, but in our experience, if you want to do 4 or 5 interlockings with the same principles, it's worth doing a formalization like this, because it's not really very deep. And while you're working with these 5 stations, it's very common that there are actually changes coming in also during the project. So if you have been doing them by hand, you had probably at some time been forced to change things you already did and redo them again. When you work generically like this, you just change what you draw on the canvas and you generate the program again. So you save a lot of time when there are changes. Taking this into account, I think the break even is somewhere around 4 or 5 interlockings.
Okay. All right. So we don't have any. Yeah. Now we have another question coming in. So let's try this one.
This software generates a root table that consists of starts and end signals. The signals should be in R, F, R, Y, F, Y. So these would be colors, I guess, aspects. The switches in normal or reverse positions and so on. Yes, we can. We have actually generated root tables for some customers, and also test sheets for some customers. You can do that. It has some limitations, though, to use tables like this, because you get signaling principles that are rather rigid, because the principles need to only use things that you can write down in a table like this. But it's possible to do. In some cases, it's more rewarding to use more dynamic principles who are not easily put into tables. But it depends a bit on your principles. So I would recommend that you actually contact us and we discuss this in your particular need.
And then we got a very good
case.
Okay, yeah. Then we got a very good question actually now in the end, because we need to close down the webinar. Will this webinar session be available online? And we are recording the webinar, and if everything goes well with the technique here, we will save the recording and we will make the recording available at least maybe in a couple of days' time. So you will, after this webinar, later today or most likely tomorrow, receive an email, and later on next week it will be available to actually see the webinar, a recorded version. And if you don't get the emails, you will at least be able to contact Jesper and Prover to be able to get access to it. So I would like to say thanks, Jesper, but a very, very warm thanks to everyone that took their time to participate on this webinar this afternoon, Central European time. So we will now close down the webinar. So thank you, everyone.
Thank you.